Hello viewers, welcome to video number 114 of the channel MALACHEMPHILIC, and this video is the 54th episode of Chemical Thermodynamics, and topic of this episode is variation of chemical potential with temperature and pressure. So let's start. Now in my last video I taught about this chemical potential where I told that chemical potential mu I of the ith component is equal to dou G by dou Ni at constant temperature, pressure and composition of other component. That means chemical potential is the partial molar Gibbs free energy, right? So this chemical potential of the ith component is nothing but the change of Gibbs free energy with change in the amount of this component of a component. Here I have taken ith component in a mixture. That means it is a mixture of number of components. Okay. So chemical potential is the change of Gibbs free energy with the change of the amount of a particular component at constant temperature, pressure and the constant composition of the other components. That is chemical potential. Okay, and this is partial molar Gibbs free energy. This Gibbs free energy is an extensive property, but this chemical potential, which is the ratio of two extensive property, is an intensive property. Remember this. So chemical potential, I write this line, chemical potential is the ratio of two extensive properties so it is an intensive property. In fact, partial molar property, any partial molar property is intensive property. Okay, fine. Now, our today's topic is how this chemical potential of a particular component in a mixture, it may be solution, it may be mixture of ideal gas, whatever it is, how the chemical potential of particular component in a mixture varies with temperature and pressure. So let's start with temperature. So variation of chemical potential with temperature. This is our topic. Okay. So let's start the derivation. Right. So chemical potential of ith component mu I is equal to dou G by dou Ni at constant temperature, pressure and other component. Right. Now differentiating with respect to temperature at constant pressure and constant composition of the components. Say this is number of components 1, 2, 3, 4 whose number of moles are N1, N2, N3 like that. We are considering that say N1 plus N2 plus N3 dot say up to Nj, that is total composition, okay, composition of the total number of moles of all the component is say N, right? So we'll differentiate this one. Now, so dol mu I by dol T at constant pressure and composition of all the components, that will be is equal to, already it is first time differentiated, so it will be dol square G by dol T dol Ni. Okay. So this one. Now, so this is my equation number 1. I write in the next page. We know that dg is equal to vdp minus sdt, right? Now, differentiating this equation, that means this one, differentiating the equation with respect to temperature at constant pressure, then what we will get? So, dol G by dol T at constant pressure is equal to, pressure constant means dP will be equal to 0, that will be is equal to minus S, right? So, say this is my equation number 2. Now, once again we will differentiate this equation with respect to Ni, that is the number of moles of ith component at constant temperature, pressure and the composition, other composition, means composition of other components, right? So, now write differentiating equation 2 with respect to Ni, number of moles of ith component we have taken at constant temperature, pressure and composition of other components. Then what we can write? This will be dol square G by dol Ni dol T is equal to minus dol S dol Ni at constant temperature, pressure, then the other component composition, number of moles of other component, like this. Okay. Say this is my equation number 3. Okay. Now, since G, that is Gibbs free energy, is an exact function, so what we can write? Dol square G dol T dol Ni is equal to dol square G dol Ni dol T. These two are same. right? Now from equation 1 and 2, see, so now from equation 1 and 2, what is my equation number 1? Equation number 1 is this one, that is dol mu I by dol t is equal to dol square g dol t dol ni. So dol mu I by dol t at constant pressure and composition, that is dol square g dol t dol ni. This one, this is equation 1. And what is my equation number 2? Equation number 2, that is, it is not equation number 2, equation number 3, sorry. This is equation number 3. What is my equation number 3? Equation number 3 is dol square g, then dol ni dol t is equal to minus dol s by dol ni at constant temperature, pressure and other composition. And what is this one? This is nothing but the partial molar entropy, that is change of entropy with respect to the change of the amount of the component I at constant temperature, pressure and the constant composition of other components. And this one, this is my equation number 3, and we know that this one, that is dol s by dol ni at constant temperature, pressure and other component, this is nothing but the partial molar entropy, which is denoted by SI bar. Okay. So here this one is equal to, that means in equation number 3, this one is equal to minus SI bar, partial molar entropy of the component I. Okay. Now look at here. This equation 1 and 3. Equation 1 dol square g dol t by dol t dol ni. Equation 3 also dol square g dol ni and dol t. Okay. And already I told you that these two are same because it is exact function. Then what we can write? We can equate these two. That means therefore what we can write? Dol mu I by dol t at constant pressure and composition, that is equal to minus SI bar. So change of this chemical potential of a component with respect to temperature at constant pressure and composition is equal to minus of partial molar entropy. Okay. So therefore conclusion is change of chemical potential of a component okay with respect to amount or number of moles of that component at constant change of chemical potential of a component with respect to temperature at constant pressure and composition is equal to negative of partial molar entropy. Okay. Now, our next topic is variation of chemical potential. Variation of chemical potential with pressure. Okay. Now let's start. See, chemical potential of this ith component. So mu I is equal to dou G by dou Ni at constant temperature, pressure and other component. Right? Now with respect to pressure. So differentiating this equation with respect to pressure at constant temperature and composition. Then what you are getting? We are getting dou mu I by dou P at constant temperature and composition, that will be is equal to dou square G by dou P dou Ni. Okay. So this is my equation number 1. Again we know that dG is equal to V dP minus S dt. So if we differentiate with respect to pressure at constant temperature, then dou G by dou P at constant temperature, that will be is equal to V. Okay. Now say this is my equation number 2. Then what I have to do? Differentiating equation 2 with respect to Ni at constant temperature, pressure and other components. Okay, means other composition of the components. Then what it will be? Then it will be dou square G, this is my equation 2. So it will be dou square G by dou Ni dou P is equal to what it will be? Dou V by dou Ni at constant temperature, pressure and other components N1, N2 ... Okay, and this term, this is nothing but this partial molar volume of ith component. Okay, because variation of this volume with respect to the amount or number of moles of component I at constant temperature, pressure and composition of other component. So it is nothing but the partial molar volume. Okay. So now you see equation 1 we got dou square G dou P dou Ni is equal to dou mu I, means variation of mu I with respect to pressure at constant temperature and composition. Similarly, here also dole square G by dole Ni dole P is equal to dole V, that is partial molar volume. So, this and these are same. That means we can equate this and this one, right? So, what we can write? We can write now, therefore, so this is my equation number 3. So, from equation 1 and 3, what we can write? We can write dole mu I by dole P at constant temperature and composition, that will be is equal to this one, that is dole V by dole Ni at constant temperature, pressure, N1, N2, all these other composition, which is equal to Vi bar, partial molar volume. So the conclusion is that variation of chemical potential of a component with respect to pressure at constant temperature and composition is equal to partial molar volume of the component. So what we have observed, that variation of chemical potential with respect to temperature is equal to negative of partial molar entropy, and variation of chemical potential with respect to pressure is equal to the partial molar volume. Okay, hope you have understood. Thank you.